Hello students, welcome back to the channel. So students, in this video we are going to study a very important topic which is Davisson and Germer experiment. This topic is from class 12th physics chapter dual nature of matter and radiation. We are going to discuss each and every detail of this experiment. Why did Davisson and Germer carry this experiment? What was the conclusion of the experiment? What was the need of the experiment? What was the setup of the experiment? So everything will be discussed in this video. But before discussing it, we have to revise the concept of de Broglie hypothesis, because only then we can understand this experiment. De Broglie said that every moving object can be treated as a wave. A wave can be associated with every moving object, and that wave is called matter wave or de Broglie wave. For example, de Broglie said that if a ball of mass m and velocity v, if a ball of mass m is moving with velocity v, we all know that a ball is a particle, a ball is not a wave. But de Broglie says that if a body of mass m is moving with velocity v, then it can be treated as a wave. So every moving object has both natures, particle nature as well as wave nature. Object is a particle, we all know that, but the new thing was that particle, a moving particle, is also a wave and not the stationary particle, right? So de Broglie said that if a body of mass m is moving with velocity v, then a wavelength is associated with this body, which is given as h by mv, where lambda is the wavelength associated with this moving body, and the name of this wavelength, it is neither the electromagnetic wave, it is nor the mechanical wave. The name of this wave was given as matter wave or de Broglie wave, named after de Broglie. Right? Here h is Planck's constant and m is the mass and v is the velocity of the body. But we all know that the wave nature associated with a ball cannot be observed simply because the value of h is very small. The value of h, that is Planck's constant, is 6.62 into 10 raised to power minus 34 joule second, and this value is very small. For example, if the ball is, suppose the mass of the ball is 500 gram. Let us say the mass of the ball is 500 gram and the ball is moving with, suppose, 1 meter per second. So wavelength associated with the ball will be 6.62 into 10 raised to power minus 34 divided by the mass of the ball, which is half kg, 500 gram or half kg, into the velocity of the ball. Let's say the velocity of the ball is 2 meter per second. So 2 gets cancelled and the wavelength associated with the ball is 6.62 into 10 raised to power minus 34, which is very small. It cannot be observed. Okay, the wavelength associated with the moving particle can be observed only when the mass of the particle is very small, which is able to cancel this term 10 raised to power minus 34. For example, the mass of electron is 10 raised to power minus 31. So if we are taking an electron for observation and not the ball, then we will put 9.1 into 10 raised to power minus 31 instead of m, right? So that minus 31 will cancel 10 raised to power minus 34 and the value of wavelength will be significant enough so that we can measure it, right? So de Broglie gave this law, de Broglie gave this hypothesis. Hypothesis is something that is not being proven, right? So de Broglie gave the name hypothesis to this law or formula or anything. So this was de Broglie's hypothesis because it was not proved at that time. It was proved using The Davisson and Germer experiment. Davisson and Germer using this experiment prove that de Broglie was right, and yes, a wave nature is associated with the moving body. So what did they do? They confirmed the wave nature associated with a moving electron or a beam of electrons. We are not going to find a single electron. So Davisson and Germer did an experiment on a beam of electrons, and they confirmed that de Broglie was right. A wave nature is indeed associated with a moving body. So how did they do it? Let's study what we are going to say. Okay. This was the setup of Davisson and Germer experiment. They took this. This is what? This is simply a tungsten filament, right? This is what? This is a tungsten filament. This was a tungsten. This F is a tungsten filament, and it is connected to a low tension battery, and this tungsten filament is coated with barium oxide. When the tungsten filament is coated with barium oxide and then it is connected with a low tension battery, low tension means low voltage battery, then it emits electron. That is its property. So when the tungsten filament is coated with barium oxide and we connect it with low tension battery, it emits electrons, right? So when we connected it, when Davisson and Germer connected it with low tension battery, it started emitting electrons. So what they did, this is a cylindrical part which is connected to the negative terminal of a battery. So it acts as a cathode, right? This is a metallic cylindrical part having a hole in between, this black one, right? This is a metallic cylindrical part having a hole in between, and this is connected to the negative terminal of the battery, so it acts as a cathode. And there is another cylinder having a hole along the axis, and this cylinder is connected to the positive terminal of the battery, so it acts as an anode. This is a cathode and this is an anode. So when the electrons are emitted from this tungsten filament, they get repelled by the negative terminal, this negative terminal, cathode, and they get attracted by this positive cylindrical part which is called the anode. So an electron gun is produced, right? Just imagine that electrons are coming out of this filament and they are being pushed away from this part and they are pulled by this part. So a gun of electrons is produced, and that gun was bombarded on a nickel crystal as a target. A nickel crystal was kept just in front of this electron gun, and when these electrons hit this nickel crystal, they get scattered in all directions. So a movable detector was present here which can move like this, and it started observing the electrons, right? Okay, so electrons got scattered in different directions, and they did this experiment at different voltages of anode and cathode. So when we have a data, when the voltage was kept as 54 volt, when the voltage between anode and cathode was kept as 54 volt, the maximum number of electrons that were observed were scattered at the angle 50 degree. This is the scattering angle which I have taken as phi because this is phi. So we are going to take theta as some other angle. I'll tell you which one, right? So the maximum number of electrons, when this voltage was kept as 54 degree, the maximum number of electrons got scattered at an angle of 50 degree. Why this is happening? Because electrons possess wave nature, right? According to de Broglie, electrons possess wave nature, and waves have a very important property of interference. So when these electrons hit the nickel crystal, they scattered in all directions, and all those scattering waves, they interfere with each other to produce maxima and minima. So this was the angle at which the first maxima was produced, and we all know that intensity in case of first maxima is minimum. So we got is maximum, sorry. So we got maximum intensity at this angle. Suppose the axis of nickel is cut at like this, at this angle, suppose theta. The axis of nickel is cut at this angle, suppose theta, and this is also theta. So if we add these three, theta plus phi plus theta, we get 180 degree. So if we put the value of phi as 50 degree, we are going to get theta as 65 degree. Now using a very important equation for crystals, which is called the Bragg's law, which says 2d sine theta equal to n lambda, where lambda is the wavelength which is bombarded, wavelength of the wave which is bombarded on the crystal, and d is the interatomic space of the crystal, and theta is this angle. So if we put all the values, the interatomic space of the crystal, and we put n equal to 1 because this is first maxima, so Davisson and Germer got that the wavelength, if these electrons behave as waves, then the wavelength should be 1.65 angstrom, right? So de Broglie also gave a formula for lambda. He said then when electrons are accelerated through potential V. Where did this formula come from? Since lambda is h upon mv, mv is what? Mass into velocity, which is nothing but momentum, and momentum is under root 2m into kinetic energy of a body, and kinetic energy is, for charges, we all know that a charge q, if a charge q is accelerated by a potential v, then energy acquired by that is q into v. So if we put the value of h, the mass of electron, and q is the charge of electron, we are going to get the value of lambda as this, right? So the voltage through which these electrons are accelerated is 54. So if you put 54 in place of v, you are going to get this answer as 1.65 angstrom again, right? So we are getting the same answer from both the formulae. This formula is typically used only for waves, but using that formula also we are getting the same wavelength which we are getting from de Broglie's equation. So this data suggested or proved that de Broglie was right, and there is a wave nature associated with electrons. So if the wave nature is associated with electrons, then obviously it is applicable to every other moving body also, right? So this confirmed that a wave nature is associated with a moving particle, right? So this was Davisson and Germer experiment. I'll meet you in the next lecture. Till then, all the very best.